one small comment before I start again. Last week I told you that for the ON model in dimension 2, you had beta c exponential that was smaller than infinity. And of course, I was thinking of the XY model. So just a correction. And it's a very important one. So for the ON model, so if n equal 1, it's the Ising model, we know that beta c exponential equal beta c magnetization, and it's finite. For n equal 2, we saw that beta c magnetization is infinity. And actually, this is also true for n larger or equal to 3. This is in dimension 2. So this is a Mermin-Wagner theorem that tells you that you did during the first semester. And I told you last week, well, in fact, you have a Kostelis-Taules phase transition, beta c exponential is finite. And I was so much thinking about n equal 2, about the XY model, that I just stated it for n larger or equal to 2, and of course it's completely wrong. So for n larger or equal to 3, the prediction, and it's maybe one of the biggest open problems in statistical physics, is that beta c exponential is equal to beta c magnetization and to infinity. So if you take the spin ON model with n larger or equal to 3, and this is a prediction, so it's a conjecture, which is attributed to Polyakov, a very, very famous physicist, is that you always have exponential decay as soon as n is larger or equal to 3. In fact, in a more general fashion, what is expected here is that if you have a continuous spin space, as soon as it's a continuous space, you have the Mermin-Wagner theorem, so you have beta c, which is infinity for the magnetization. And the prediction is that if the Lie group is commutative, then you are in the Kostelis-Taules phase transition, and if it's non-commutative, you are in a phase where you have always exponential decay. This conjecture is completely open. It's a very big open question and a very interesting one. So I just wanted to correct because what I said was wrong. Simply. Yeah.
What do you mean if the Lie groups commute that most of the SNs are in groups, right?
Yes, but sorry?
Most of our spin space is Sn?
Yes.
And that's only a Lie group when n is like 1 or 3.
Yeah.
Okay, so what about n much larger?
No, okay, let's discuss that overall. Okay, so that was that's the correction I wanted to make. So, do you have questions about the first lecture, except the fact that? No? Okay. So we keep going with the second lecture. So we finished on the Edwards-Socal coupling. So I just remind the coupling. Which was saying that, I mean, I'm not restating completely, but if omega is sample according to the random cluster measure on G with parameter P and Q, and if sigma is coloring of the clusters, and it was a uniform random coloring of the cluster, so you give one of the Q spins to every cluster, meaning to every vertex in the cluster, then sigma is sample according to the Potts measure on G with parameter beta. So Q is the number I mean, Q here denotes the Q state Potts model, where beta was equal to minus Q minus 1 over Q log of 1 minus P. Okay, that's what we prove. So this is for this measure. Now, what do we do when we have, so remark, what do we do when we take a positive? So here we remember that we also introduce a magnetic field. So here I claim it was for zero magnetic field. What do we do when we have a positive magnetic field? So this was one of the exercises, which I'm certain everybody did, since I just saw that basically all the pieces of paper were still in my... That's the problem with, good old exercise sheets, is that I can count how many of you took the thing. So, if you want to have a coupling with the H positive, what you do is you take your nice graph G. I mean, it's maybe a nasty one, but that's fine. Okay. You take your graph like that. And what you do is you add an additional vertex outside your graph, which you call the Ghost Vertex. Okay? This is just a reference to Griffith, who introduced this in another context, but which can match with this one. So you add the vertex, and this vertex you decide to glue it, to connect it by an edge to every single one of the vertices in your graph. Okay? So you introduce a new graph, so G gives rise to a graph G ghost, that I will denote it like that. And here, the vertex set is a vertex set of G union the ghosts. And the edge set is the edges of G union the xg for x in V. Okay? So you add a vertex, you connect it to every element here. Now, you define a random cluster model on this new graph. Okay? So let's call it, this will be the random cluster measure on this graph, where every edge has vertex set P. So what I'm going to add is I'm going to add an edge here, and by this edge I mean the random cluster measure which gives you P over 1 minus P to the number of open edges, Q to the number of clusters in omega, except that here it's the number of open edges in E of G, and I'm just going to add here a E to the, to the number like that, where this is the number of open edges of the form xg. Okay, so you still count P over 1 minus P to the number of open edges in omega, in the standard edges, and you put a e to the edge minus 1 to the number of open edges, orange open edges like that. Okay? So it's kind of an inhomogeneous random cluster model. If you forget the Q to the number of clusters, what does it give you? It gives you a percolation model, as before, except that the probability of an edge to be open here is P, and here it's 1 minus e to the minus h, right? This thing, you can rewrite it as 1 minus e to the minus h divided by 1 minus e to the minus h, meaning this thing, right? So when h equals 0, probability of an orange edge to be open is 0, and you recover just a percolation model on the graph G. But as soon as edge is positive, you get really a nice model on this thing. Okay, so there was a quantity that we were very much interested in, which was sigma 0 scalar product with 1, with the spin 1, which belongs to our graph, right? And we were looking at it in G, beta, H, and here I'm going to remind the Q to say that I'm looking at the Q state pots model. Can somebody give me, or does somebody has an idea, how to couple this model with this one, this random cluster model, and how to reinterpret this in terms of connectivity properties of the random cluster model? Yes?
So you color all vertices attached to the ghost Wagner?
Yeah.
And all the other clusters you uniformly color?
Exactly. So I found the only person who took one of the piece of paper with the exercises. Good. Indeed. So what you do is you do exactly the same as on this graph, except that you force the cluster of the ghost to receive spin 1. Okay? If you do that, so here you sample omega according to phi g ghost p h pqh, sorry. Then you color every vertex, every cluster at random, except the cluster of 0, which receives spin 1 automatically. So this one you don't sample at random. Now, what? In the cluster of G. Yes. If you do that, what do you get here? Well, if 0 is not connected to the ghost, then its spin is taken at random. Its average in the case of the Q state pots model gives you 0. Therefore, you get 0. If it's connected to the ghost, then the spin automatically is 1, and the scalar product of 1 and 1 is 1. So this thing gives you exactly the probability that 0 is connected to the ghost. Okay? So you can also reinterpret the magnetization using this construction. Okay. Let me now, and this is going to be most of the class today, try to use the random cluster model to deduce monotonicity properties of spin-spin correlations. Okay? So let me just check that I didn't forget any. No, okay, good. So this is small c. Okay, I'm already lost with every year I think that I'm going to be super good at numbering things, and then I'm confused after exactly one lecture. This is small c or small 3? B? B. I don't know how I got to B, but that's fine. Okay. B. Monotonicity properties. So you are going to see maybe you are going to feel like this is kind of trivial, and I mean, maybe not trivial, but that of course something like that should be true. I should say that I'm studying the Potts model in this class. I could try to study other statistical physics, I mean, spin models. Actually, the thing that breaks down very quickly is this monotonicity property. So it's a kind of very delicate property, and we are lucky enough that the random cluster model has this property, but it's not at all something general in some sense. Okay. So, what do I mean by that? So let's forget for a moment about the Potts model and focus about on the random cluster model. And let's notice a very simple thing about Bernoulli percolation. Okay? So for Bernoulli percolation, so this is kind of a motivation for Bernoulli percolation. There is a natural way of coupling the Bernoulli percolation measures at different values of P. Meaning that if I take P smaller than P prime, and if I sample two configurations, one, so sampling two configurations, omega P and omega P prime, according to P and P prime. So I don't remember if I wrote that, but this for me means a Bernoulli percolation measure with parameter P. I think I mentioned it last week, but it's just I prefer, it's rather than writing phi GP1, I prefer this notation to be certain that we are talking about Bernoulli percolation. So if you sample two configuration omega P and omega P prime, a thing that you would like to have is you would like to have that this every open edge here is open here. Why? Because P prime is larger than P, and you feel that the larger the P, the larger the configuration. If you do it stupidly, I mean, I'm not saying people are stupid, but I mean, if you just sample two independent configurations, then there is a probability P times 1 minus P prime that the edge is in fact closed in omega P prime and open in omega P. So taking two independent configurations is not a very good way of coupling things. But there is a much cleverer way of coupling omega P and omega P prime, is to use the following measures. So define the coupling P by the following formula. So consider uniform. So if you think this is trivial, I mean, the next thing will be non-trivial, so don't worry. So consider a uniform random variable, UE. So UE is a uniform random variable on 0, 1. And ask that these guys are independent. And now define omega EP to be equal to 1 if UE is smaller than P, and 0 otherwise. Okay? If you define omega EP like that, what you notice is that for every fixed P, the probability that omega P, maybe I should put a superscript here, omega P is open with probability P and closed with probability 1 minus P. And the second thing that you observe is that the omega PE are independent of each other because the UE are independent of each other. But the good thing with this coupling is that you can define all the omega P from the same UE, and you automatically get that omega EP is smaller than omega EP prime. Okay? So you define the probability space on which all the omega P exist in such a way that omega P E is smaller than omega E P prime. Question: can this be done for the random cluster model? Can one construct a probability measure P coupling, say, phi G P Q and phi G P prime Q in an increasing manner. Okay? Question mark. Of course, here P prime is still larger than P. And you are going to see it's possible in certain cases, but it's definitely, I would say, less elementary than this trivial coupling for Bernoulli percolation. Okay. So a definition, and then a theorem. So definition, we said that mu and nu, okay, for two measures, mu and nu on 0, 1 to the edges, we say that mu is stochastically dominated by nu if there exists such a coupling. If there exists a probability measure P on 0, 1 to the edges times 0, 1 to the edges. So it's a probability measures on pairs of configuration. So in a standard fashion, I will say that omega belongs to that and omega prime belongs to that, such that if omega prime is sample according to P, okay, so if the law of omega prime is P, then three things. The first two are going to just say that P is a coupling between the random cluster measure at parameter P, between mu and nu, sorry. So I'm going to say that omega is sample to mu. So the first marginal is sample to mu. The second marginal is sample according to nu. And the third property is going to be this increasing property. So it's going to be that omega is smaller or equal to omega prime P almost surely. Okay? So we say that mu is stochastically dominated by nu if there exists an increasing coupling between the two. Okay? So an example, of course, is this. This is an increasing coupling between the Bernoulli percolation measure of parameter P and the one of parameter P prime. Therefore, P, the percolation measure at parameter P is stochastically dominated by the one at parameter P prime. So maybe a remark why this is going to be an interesting property. Let A be an increasing event. Okay? Or let's start with something. Let X and Y belonging to G. The probability that X is connected to Y. How does it compare to the probability, for mu, how does it compare for the same probability for nu? One thing that you can do is you can say, okay, by definition, by this property, by property 1, this is equal to the probability that omega belongs to X connected to Y, right? This is the definition of the first marginal has low mu. But here, what I know I can do by the third property is that I can assume that omega is smaller than omega prime. By the way, this is clear for everybody what that means, right? This is just the ordering on 0, 1 to the number of edges. So that means that omega e is smaller or equal to omega prime e for every e. Or in other words, every open edge in omega is open in omega prime. So here I can assume that this is true. But notice that as soon as omega has a connection from x to y, and omega prime is larger than omega, what do I deduce? That omega prime has a connection from x to y. So it's not an equality, of course, but it's an inequality. And this is nu of x connected to y. So imagine, for instance, that mu will be the random cluster model with parameter p, that nu would be the random cluster model with parameter p prime larger than p. Okay? Let's say q is an integer. This is what? This will be the spin-spin correlation for the Potts model. So what this thing would tell you is that the spin-spin correlation at a parameter beta, which corresponds to the first p, would be smaller than the spin-spin correlation at parameter beta prime, which is associated to p prime. So that would tell you monotonicity of the spin-spin correlation for the Potts model. So our whole goal is going to be to manage to prove this. That's going to be the goal of today. Just another remark. Imagine that here I replace this by a general event A. What do I need on A to be able to make the same sequence of inequalities? You need indeed that A is increasing, meaning what? Here I need to be able to deduce that if omega is in A and omega is smaller than omega prime, then omega prime is in A. Okay? So I'm going to define, say, let A be increasing, meaning exactly this, that omega in A and omega smaller than omega prime implies omega prime in A. If you have this assumption, then you have this property. How can I rephrase this thing? I can also say the indicator function of A is an increasing function. Here maybe another way is to say indicator of A is increasing. So indicator of A is a function from 0, 1 to the number of edges into 0, 1. So there is a perfectly well-defined order for this type of functions. And increasing means increasing for this order. Okay? So I hope I managed to motivate at least this notion. So let me give you a criterion that allows you to construct a coupling which is increasing between mu and u. So lemma assume that for every edge in your graph and every configuration psi in 0, 1 to the edges of your graph minus e. Okay, so I give myself a configuration outside E. Assume that mu of omega E equal 1, knowing omega F is equal to psi F for every F not equal to E. So I'm taking the probability that the edge is open, knowing that all the other edges correspond to the configuration psi. And assume that this is smaller than nu of omega E equal 1, knowing omega F is equal to psi F for every F. Actually, maybe I'm going to give myself two configurations, sorry. So I give myself two configurations psi smaller than psi prime, and I assume that I have this monotonicity. Okay? So the probability of being open in the small, what we think as a small measure, when I condition everybody outside to be equal to psi, is smaller than the probability of being open in the big configuration, knowing that everything outside is equal to psi prime, and psi prime is bigger than psi. Okay? If I have this property, I claim that I can construct a coupling. Then, then mu is stochastically dominated by nu. Okay. So in order to prove this, what do I need to do? I need to construct by hand, if you want, a coupling. And there are not so many ways of constructing a coupling. One of them, if you want to construct, even if you want to construct a measure satisfying a certain property, one way of doing it is to construct this measure as a stationary measure of a certain Markov chain. And here it's exactly what I'm going to do. I'm going to construct a Markov chain, and I'm going to make this Markov chain in such a way that the P that I'm trying to construct is a stationary measure for this Markov chain. And this Markov chain will have the following property, that if I only focus, so it will be on pair of configuration, and I would like that the first marginal is exactly evolving in such a way that the only possible stationary measure for this Markov chain will be mu. The second marginal will be made in such a way that the evolution is necessarily leading to nu. And then what I would like in my steps of my Markov chain is to guarantee that if I start from a configuration omega 0, which is smaller than omega prime 0, then it will remain so for the whole evolution. That the increments are such that you keep the ordering. Okay? So how do I do that? So I'm going to make something a little bit more complicated than for Bernoulli percolation. So give yourself I'm using chokes as there are cliffs that are afraid of me, you know. I destroy so many chokes. Okay, give yourself a family of independent, uniform 0, 1, random variables. So you think this is exactly as before, but not quite. I'm going to give myself this time uniform random variables that are both indexed by the edges and the integers. Okay? I'm thinking, this evolution is going to make, I'm going to choose at random edges and then increment things at these edges. So I will use for the kth increment at the edge E, the random variable U, E, K. Okay? So that's the first thing I want. And I want also uniform, I want also, exponential clocks at every edge. Yes, so I will exponential clocks at every edge. what do I mean by that? I maybe don't want to formalize it too much, but I want is that at every edge there is an exponential random variable, and every time it rings, I'm going to increment. Okay? So another way, yeah. I mean, is it clear, or should I say I want a family of exponential random variables?
Should they be Poisson distributed instead, since we have natural time parameters?
Well, yeah, Poisson maybe. Natural time. Oh, no. Let's take exponential because I would prefer that they don't ring at the same time. Okay? So at every edge, you have an exponential clock. Actually, you have infinitely many exponential clocks. As soon as one rings, you start the next one. And now, yeah. Sorry?
Can you write down what you do like this?
Okay, yes, I can. Okay, so what you mean is that you give yourself exponential EK, which are exponential clocks. I'm hating you right now. Asking me that on a Monday morning. You have no consideration for my age. I mean, for you, I mean, this you are still a student. Thursday evening is a bad day, right? I mean, Friday morning is difficult, but for old people like us, it's a weekend, which is difficult. Okay, so you put exponential, just parameter 1, random variables, okay? And now I'm going to, yeah, okay. And now the evolution is the following. At time, so yeah, actually it's not going to be that bad. At time t, which is sum of the exponential e, I mean, t e k, which is this thing, for, if you don't understand anything to what I'm writing, blame him, okay? So at the time where the kth clock at the edge E rings, which is this time t, do the following. You resample every edge according to the following. So omega t and omega t prime t are going to be the Markov chains. They are going to start at omega 0, omega prime 0, which I'm going to tell you later what it is. Or maybe I should start by that. No, later. So I'm just telling you how it evolves. So at time t, resample both things according to the following. I'm going to tell you when it's equal to 1, when it's equal to 0. Okay? So it's going to be equal to 1 here if mu of omega, so let me just see how I wrote it. Yeah. If the uniform random variable uk is larger or equal to the probability that omega e is equal to 0, knowing that omega on the edges except e is equal to omega t minus, I'm going to tell you what this is, and 0 otherwise. So what does it mean? Omega t minus is a configuration just before time t, okay? Like at an infinitesimal time before time t. If you want, it's the limit of the omega s when s tends to t from below. Okay, so you have a configuration just before the jump, and you resample the edge E by saying it's open if the kth uniform random variable associated to E is larger than mu of this. Notice that what is the probability that your edge is going to be open at the end? If you want this uniform to be larger than this, you immediately see that the probability of being open for this edge is exactly the conditional probability of being open knowing this configuration, this conditioning. It's exactly made in such a way, right? So here, the resampling is exactly made in such a way that if I know this, if I know that everything outside is equal to omega t minus, then I resample the edge at E exactly in such a way that it's going to be open with the right probability and closed with the right conditional probability. Both things. Okay? And I do the same for the other one, this time with nu. But according to the new thing. Again, the resampling probability is made in such a way that the probability that this edge is open knowing the conditioning is the right one according to nu. Okay? I told you it would be harder than the copying for Bernoulli percolation. Okay. Notice, this is a remark, that if omega t minus is smaller than omega prime t minus, then what do I deduce? This is larger than this. So this thing is smaller than this thing. With a 0, this thing is larger than this thing, right? It's 1 minus this probability. Right? If I put zeros, then the inequality in the other direction. So this thing is larger than this thing. Therefore, if omega prime E is equal to 0, then this guy is also equal to 0. So you keep the ordering. So if this is true, then omega E t is smaller than omega prime E t. Okay, so what do I do now? So if one starts with omega 0 equal 0 and omega prime 0 equal 1, then omega t is smaller than omega prime t for every t. I preserve the ordering along the whole thing. Okay? So I have a Markov process, right? This is a continuous time Markov process. It has the property that you always have the right ordering. By the way, it's well defined, so why do I take exponential clocks instead of Poissonian clocks, for instance? Is that notice that every time here, if you have a time of this form, it's going to be of this form only for one edge. It cannot be that two edges are going to ring at the same time. Really think of that as the time where the kth ring on the edge E. The time of the kth ring on the edge E. And what I'm claiming is that there is not a single real number which rings at the same time in two places. Why it's important? Because here I want to be able to define my configuration in such a way that there is only one ring to be able to do this resampling. Okay? So I keep the ordering, and as I said, the resampling is exactly made in such a way that it's the right resampling for the measure mu here and the right resampling for the measure nu here. Another way of putting it is that imagine that instead of starting with omega 0 equal to the configuration equal to 0 everywhere, imagine I start with a measure sample according to the random cluster measure. According to mu, sorry. if I start according to mu, the resampling is going to preserve mu. So mu is a stationary measure for omega t. Nu from this thing is a stationary measure for the Markov chain omega prime t. Now, these are Markov chains. It's very easy to check that they are irreducible. I let it to you. Or, I mean, I should rather say to Franco. So you can check, and then Franco can help you if you are having difficulties. Yes, I'm going to put all the dirty work on you. That's why PhD students are for. So they are. I said they are irreducible. An irreducible Markov chain has a very nice property that it has a unique stationary measure, and it converges to this stationary measure when t goes to infinity. Since mu is a stationary measure of omega t, nu is a stationary measure of omega prime t, well, then what I can do is define P to be the law, the joint law of omega infinity, omega prime infinity, meaning the limiting thing, or I mean, to be more precise, just to define Pt to be the joint law of omega t, omega prime t, and P to be the limit when t tends to infinity of Pt, limit in terms of weak convergence. And this P will therefore have the property that, well, the law of omega will be the limiting law of the omega t, meaning mu. The law of omega prime will be the limiting law of omega prime t, it will be nu. And because I have this ordering property for every t, of course I get it for the infinity, for the limit at infinity. Yes? Sorry? Yes, and the measure should be positive, yes, which is the case. You see, he's much better at it than me, so that's perfect. So, the measure P satisfies all the properties of our coupling. Of course, I could spend like 1 hour justifying all the small steps, but I mean, the goal is not to be too slow on these things and to get to more exciting stuff. Okay, we are going to do a break and restart at say 20. So what will we do in the second part of the class? Well, we are going to check this criterion that I just erased as a stupid person. So this criterion is going to be satisfied in certain cases, and you are going to see it's going to give us very nice properties, not only ordering, but even nicer properties. Okay, good? Coffee? Okay. So, are there questions on the first hour? Okay, so let's deduce something for the random cluster measure. Hop-là. So, theorem. So fix Q larger or equal to 1. And this is going to be very important. Then we have the following properties. So the first property is, if you want that, it's stochastic domination. So if P P smaller equal to P prime, so phi G P Q is stochastically dominated by phi G P prime Q. Second property, phi G P Q is stochastically dominated by phi G ghost P Q H. Okay? And third property, for any increasing event B, phi G P Q condition on B, so the random cluster measure condition on the event B. No, sorry, up. This one is stochastically dominated by phi G P Q condition on B. Okay? So you understand when you read this theorem that what we are going to do every single time is checking the condition of the previous lemma, right? But before that, I want to tell you a little bit more about these different properties. So the first one is exactly the one that I mentioned before. It's going to be the monotonicity in the parameter P. It's going to have a lot, many implications, but I'm going to state them after the proof. Or maybe I state all the implications before the proof and then the proof. So, remark. First thing, so phi G P, property 1. Let's go then P1, P2, P3. So P1 is called monotonicity. Monotonicity. So first thing it gives you is that you remember we defined beta C exponential. It's called monotonicity applied to integer Q. What does it give me? It gives me in particular that sigma x, sigma y, G beta Q is increasing in beta. This I justified before because the point-to-point connection is an increasing event. So if I have stochastic domination, I have that that phi P of beta Q of x connected to y is smaller than phi G P of beta prime Q of x connected to y. Right? Because it's easy to check from the formula that beta smaller or equal to beta prime implies P of beta smaller or equal to P of beta prime. No? This is, you can let your little brother check that. Other application, sigma x scalar product with 1 is increasing in beta. Exactly the same argument, right? Wait, yeah, I didn't say, but here you can also, if you like it, put the ghost. So maybe I should add. Edge here should be positive. Huh? So you can also put the ghost, and therefore here it's the same thing with x connected to the ghost, right? So what does it imply, these two properties? It implies in particular, what do you get? You remember beta C mag was, what was it? The infimum? No. I should remember what is my definition. I chose one of the two, so beta C was the infimum of the betas, such that mag right? It was the smallest, I mean, the infimum of the beta for which the spontaneous magnetization was strictly positive. But the fact that this is increasing in beta implies that this is also the supremum of the beta such that non-magnetization. Right? This was not clear a priori, but now that we have monotonicity, it's clear. Other property that it implies, given by this, beta C exp, which was the sup of the beta such that exponential property, such that the spin-spin correlation were decaying exponentially fast. Well, this is also the infimum of the beta such that non-exponential, and you deduce, I mean, you guess what I'm going to say for the last one. This was the infimum of the beta such that long-range ordering, and it's in fact supremum of the beta such that I don't get this property. So all these properties, I mean, another way of putting this is that all these properties are increasing, are written in terms of increasing properties. Therefore, as soon as they start holding, they will keep holding forever. Or as soon as they stop holding for exponential, they will stop holding forever. So there is a good, I mean, it's really, these parameters really distinguish between two phases. It's not that it's alternating between several phases. This is something very intuitive. I think nobody even expected that, okay, you start have magnetization and then you could stop again having magnetization. But this has to be proved. And that's, that follows from these monotonicity properties. That's a comment on the first property. Just a comment on the third one. So P3, as soon as you have stochastic domination, what do we know? We know that for any A increasing, phi G P Q of an increasing event, A, is smaller than phi G P Q of A knowing B. But A knowing B is the probability of A intersected with B divided by the probability of B. So here I can rephrase this like that. Right? That's a way of rephrasing my property P3. Well, this is called the Fortuyn-Castellan-Guinibre inequality, F Kg inequality. And this is one of the most important inequalities in probability. So this is called the F Kg inequality. So the random cluster model was defined and introduced by Fortuyn and Castellan. And they noticed in the second paper with Guinibre that this inequality holds for this random cluster model, and that's why it's called F Kg inequality. For people who did Bernoulli percolation, they saw the Harris inequality, which is the equivalent of the F Kg inequality in Bernoulli percolation. Okay? If you ask what is strong or powerful about probability, it's not something very easy to answer to a non-probabilist. But I would say that there are two things that are really important. The comparison to measure theory is the notion of coupling. I think the notion of coupling is really one of the most marvelous things in probability. And if you compare the probabilistic approach to more analytical approach to the Ising model or to statistical mechanics in general. We will see actually other approaches in other chapters of this class, is that historically the approaches to statistical mechanics were much more analytic in nature. So what is the strength of probability compared to these analytic approaches? That it can use much more inequalities. And this F Kg inequality is an archetypical example of something which is powerful for probabilists and very useful, and that can lead to many arguments that are very difficult to get if you do not use this monotonicity argument. So this is absolutely fundamental inequality. If you don't have it, you are in trouble. I mean, I'm in trouble. Maybe smarter people can do things, but I'm completely in trouble without the F Kg inequality. So I love the F Kg inequality. If you say something bad about it, so you are in trouble. Okay, very good. What else did I want to say about these things? I think I already said enough. So let's go to the proof. We start with the simplest, with the first property. So we need to check the criterion for the mu and nu. Okay, so in the first inequality, mu is going to be the random cluster measure at parameter p, and nu the random cluster measure at parameter p prime. So let me just try to see what is the probability of omega e equal 1, knowing omega f equals psi f for every f not equal to e. Right? Because this is exactly what is entering in the criterion. So this is equal to what? We can take two values depending on psi. So what are these two values? Imagine that the two endpoints of the edge E are connected to each other in psi. Okay? So if x, so let's say E is an edge xy. So imagine that x is connected to y in psi. This thing is a big ratio. It's a ratio of the sum over every configuration, and in this case there is only one, which is equal to 1 at E and to psi for every other edge, of p over 1 minus p to the number of open edges, q to the number of clusters, divided by the sum over every configuration, which is equal to that outside. So there are two configurations, one closed, one open, of p over 1 minus p to the number of 1. Notice that if psi is such that x is connected to y, the q to the number of clusters, well, is the same on the top and on the bottom. For all of the three configurations, I mean, there are two configurations involved, right? The one which is equal to 1, the one which is equal to 0. The cluster count is the same in both configurations. The status of the edge E doesn't change the cluster count. So what you are going to end up is p divided by, well, p for the configuration where the edge is open, plus 1 minus p in the case of the configuration where the edge is closed. So you end up with p. I'm not very clear here because this is one of the exercises and I don't want to spoil all the fun out of the exercise session. So you will check more carefully that if x is connected to y inside, you get p. If x is not connected to y inside, what do you get? If the edge is open, or if the edge is closed, now it does change the cluster count. There is one less cluster when the edge is open. So in this case, when you are going to do your computation, you are going to get p for the configuration where the edge is open. But instead of just getting 1 minus p in the case of the edge closed, which was giving us the 1, you have one more cluster in this case. So you get a q like that. Okay? So you will check in Franco's class that this is equal to this thing by really writing the whole. Yes?
Can you take you call this finite energy? Like in the exercise,
Did I use finite energy?
finite energy on top of this exercise. And I don't.
I said that in the... Because you see, one thing which is important is that whatever, so what we call finite energy, is that whatever the conditioning you put on, the probability of an edge to be present or close is non-degenerate. It's strictly between 0 and 1. There are, you can imagine percolation models where this is not true. I'm going to give you two examples. The first example is imagine that Q tends to 0 in the random cluster model. So I'm doing a parenthesis, it has nothing to do with this thing. When Q tends to 0, what you are forcing is what? You are concentrating on just a configuration where there is only one cluster, right? You force this to have only one cluster because Q is, only the case with minimal number of clusters will be fine. But then imagine that I give you a graph that looks like, I give you a graph that looks like that, and here I have my edge E. And I tell you all of this is open, all of this is open, and all those are closed, say. Let's say it's a piece of the square lattice. All these edges are closed. For Q equals 0, for the limit Q equals 0, this edge here will be forced to be open because I want a unique cluster. So it's a case where you don't have finite energy in the sense that this edge cannot be closed. The probability of this edge being closed is 0. So this is a percolation model which doesn't have the finite energy property. Another percolation model that you can think of is called the uniform spanning tree. What you do is you sample uniformly at random a spanning tree in your graph. Meaning what? It's a tree, and it needs to visit every vertex in your graph. This guy, you can check that if I condition on the state of all the edges outside one edge, for instance, and that I already see a spanning tree, so these two endpoints need to be on the tree, then this edge cannot be open, because otherwise it will create a loop. This is another example of a percolation model that doesn't satisfy the finite energy property. You have much more natural models like that. These are natural models, but maybe not related to standard spin models and things like that. But you have other models that have this, that lack this property. So that's what finite energy means, and it's a very useful property, in particular for those who saw the proof of the Burton-Keane argument, the uniqueness of the infinite cluster. I will talk about it next week. This finite energy is a very important property there. Okay. So that was a parenthesis. Okay, so once we have that, in fact, so for P1, well, the proof is fairly simple, right? Because if you fix Xi smaller than Xi prime and P smaller than P prime, then the conditional probability of an edge is open knowing omega f is equal to psi f for every f not equal to E. Well, so either this thing is equal to P, but in this case it's always smaller than P prime and P prime, either this, so if this is equal to P over P plus 1 minus PQ, then that means that it's automatically smaller. Then this has to be smaller than phi g P prime Q of omega E equal 1, knowing omega f equal psi f for every f not equal to E. Why? Because this is equal, remember, to P prime or P prime over P prime plus 1 minus P prime Q. And notice that this is always smaller than both things. This is an increasing function of P, so this has to be smaller than this. And this is smaller than, this is larger than this because Q is larger or equal to 1. Okay? So if this, then that, and if it's equal to P, well, what does it mean? It means that psi must have a connection from X to Y. And therefore also in psi prime, because psi prime is larger or equal to psi, and therefore this guy is equal to P prime, which is larger than P. So in both cases, you are certain that you have the right monotony, CT. Okay? Is it fine? I'm not going to ask whether it's clear because that's I'm not going to enjoy the answer. But it's fine. But, it's a safer thing. Okay. P2. Well, P2 you can check that for every edge. I mean, of course, P2 I kind of said something which was maybe not completely clear. Is that I said that phi g, I mean, I don't remember what I said for P2. P2 was phi g pq is stochastically dominated by phi g with a ghost pqh. Let's be careful, these two measures are not defined on the same probability space. So I forgot, and maybe you should add it, that when I mean stochastically dominated by the other measure, I mean the other measure restricted to the edges in G. Like that, these are two measures on the edges in G, and I can compare them. Then there, you can just do exactly the same comparison, and just notice that in the bigger configuration, these additional edges can only help you to create a connection. So it could be that X is connected to Y in psi. I mean, that X is not connected to Y in psi, restricted to the graph G. But that with the additional ghost, they get connected to each other. But this is only helping you. So it goes the same direction. So this may be fine as well. And for P3, well, for P3, in some sense, I kind of lied a little bit. Because I need to do what? For P3, I need to compare this measure and this measure. So when you are going to do the same computation here for these two measures, the only thing is that sometimes in this measure, so here it's always P and P over P plus 1 minus PQ. Here, the difference is that sometimes you are not allowed to be close. Why? Imagine, so here, if I add, so the only difference with this thing, and that here, I'm also assuming this, right? I want omega to be in B. But it could be that the psi is such that if omega E is closed, so omega F is equal to psi F for every F not equal to E, but at the edge E, omega E is 0. It could be that this is not in the event B, right? If it's not in the event B, how does it change here? Well, if it's not in the event B, just the probability that omega E is 0, knowing this, is 0. So in this case, it could be if the configuration omega equal to 0 on E and psi E, psi F for F not equal to E, if this doesn't belong to B, then the answer is that automatically for this measure, the edge E must be open. So this is 1 and this is 0. But then when you compare the P over P I mean, these two probability measures to these two things. Sorry? Sorry? Sorry, both ones. Both ones. Thank you. Yeah, well, it doesn't depend on, well, okay. So, either you are not in that and this is a crossing, this is a thing, or either you are in that and then the probability is 1. I'm going to put it here. Yes. Okay?
Could we possibly have, so the way we've stated it so far,
yes.
We compare some conditioning on the outside called psi and some other larger conditioning on the outside called psi prime, which is arbitrary but larger than psi.
Yeah.
But not every psi prime might satisfy B.
Yes, so that's very good. So you are exactly getting to my next sentence.
Okay.
So this is true as long as it's even possible. I mean, this is true as long as the configuration with 1 at E and psi outside is in B. If none of the two is in B, then somehow you would like to be saying that you will get 0 probability for both. But notice that the conditioning also would be degenerate. What happens is that the measure condition on B is not a positive measure on all of 0, 1 to the edges. This measure is 0 outside of B, and it's positive only on B. So in fact here, when I said that I lied to you at the beginning of this P3, is that the lemma we proved was not quite sufficient, because I was only looking at measures that were positive for every edges, which I didn't tell you. But that's the difference between a first year class and a master class. Anyway, you have to reconstruct all the mistakes that I'm doing. Think of this as a message of hope, that you can do research while making mistakes at every statement. That's don't record that if possible. Okay, so what was I saying? Yes, so it doesn't, I mean, it looks like the lemma is wrong. I mean, doesn't apply to our setting, except that, remember, I said something. I start with omega 0 equals 0 and omega 1 equal 1. Right? 1 everywhere. Omega prime equal 1. So notice that here in the previous lemma, omega prime 0 was equal to 1. And notice that this guy belongs to B as soon as B is non-empty. If you take an increasing event which is non-empty, then by definition it contains one configuration. But if it contains this configuration, it contains any configuration larger or equal to this configuration. And of course, the configuration equal to 1 everywhere is one of these configurations. So omega prime 0 is in B. And if you think about it, then if you resample every time a clock ring, you resample according to the conditional measure, right? You resample according to nu. Then you are always going to remain in B. So in this case, the only thing you need to prove is you need to prove that you are irreducible on B. That you can go from any configuration in B into any configuration in B, and that will give you a unique stationary measure that is supported on B. So the coupling actually works. And I can see that nobody is convinced. That's fine. So in a, and the Markov process is an irreducible Markov process on the omegas in B. Thus, it has a unique stationary measure which is exactly phi g p q knowing B. And now here, the only thing you have to satisfy is you have to check that for any configuration psi smaller than psi prime, where psi prime is such that when I put an open edge, I'm in B, I satisfy the inequality, and this is exactly this thing. Don't agonize on that. I mean, it's fine if this is not clear. I know there is an exam at the end and blah, blah, but I promise that if I cannot write properly proof, I'm not going to ask you to write it. This is, so every time you feel like I'm skipping steps and so on, you know already this is not going to be something that... Okay. Yes, the exam will be a written exam, and there will not be anything about, I mean, I should not say that, about the class. I mean, it's going to be exercises, really, like something fun to do. I mean, fun for me and Franco to do, and very stressful for you. But okay. So this is the proof of the F Kg inequality. You can try to write it from A to Z. It's actually a very good exercise. And the thing that I want to keep from that is just keep the statements, so the monotonicity and the F Kg inequality. This we are going to use a lot. Okay? I'm thinking that I'm not going to start the next section because in 5 minutes I will not go very far. So what are we going to do next week? So next week, we are going to define, using this monotonicity properties, we are going to define infinite volume measures. Okay? Okay, so maybe we are going to define infinite volume measures. And we are going to prove that these measures are nice in the sense that they are invariant under translation, they are ergodic, and so on. And this will allow us to re-express in a nicer way, maybe, the magnetization property and the long-range order property. And then we are going to prove that beta C long-range order is equal to beta C magnetization. In the lecture after that, what we are going to do is we are going to prove that beta C exponential is equal to beta C magnetization. So in some sense, at the end of that, we would have proved that for for Potts model, the 3 parameters are equal. The lecture after that, so in 3 lectures, we are going to compute beta C for the square lattice. You can think, okay, good, then lecture after that for Z3, after that for Z4, and so on. It's going to be a very boring class. Be safe. We don't know how to compute the critical parameters in dimensions 3 and more. So you are going to be safe with that. We are just going to do beta C on Z2. And then after that, we will change completely and work on another subject, and I will show you another type of thing. Let me just conclude because maybe I should have mentioned it even in the statement, but I wanted to go fast. So, remark. P2 is a special case of the following general statements. Imagine that I defined a measure which is a measure where P bar is just a collection of PE for E in the edges. So I'm going to define the random cluster measure which is inhomogeneous. There are different edge probabilities. So the probability of a configuration omega is going to be 1 over Z G P bar Q of the product over the edges of P over 1 minus P to the omega E times Q to the number of clusters. So notice if Q equal 1, If Q equal 1, what does it mean? It means that every edge is open with probability PE. Okay? If you run the whole argument, do you agree? I should not state it like that, but do you agree that phi G P bar Q is stochastically dominated by phi G P bar prime Q, where P bar is smaller than P bar prime? What we just use is that at every edge, we had this P smaller than P prime. So you have this thing automatically. Do you agree? Okay, so in particular now, imagine that H is a graph which is larger than G. G is smaller than B. Then phi G P Q, how does it compare to phi H P Q? So the same P, but on a bigger graph.
And G is restricted to Q.
Yeah, thank you. I'm going to learn, but okay, yes, restricted to G to have the same probability space.
It's bigger for G.
Sorry?
It's bigger for the smaller graph. Like,
Too bad, 1 out of 2 chances.
it's like if you put 0 on all the.
Yes, this one is like this one, but where I put 0 on other edges. 0 is smaller than P. Therefore, this guy is stochastically dominated by this one. Ah, I see that somebody also thinks, oh, no, no. I promise it's in this direction, okay? So the bigger the graph, the bigger the measure. So this is something very different to Bernoulli percolation. In the case of Bernoulli percolation, you can make your graph bigger and bigger. The measure, well, it doesn't decrease, but it's always the same, the percolation measure on the thing. Here, we still have that it's not smaller, but in fact, it's even bigger and bigger in many cases, okay? But the only thing I want you to remember is that you have this ordering also at the same P in the graph. And in some sense, this was, P2 is a special case where your graph is with an additional ghost, and you get this 1 minus e to the minus h for the PE. Okay? Very good. I hope to see you again next week. And until then, enjoy.